guys, welcome to chapter 7 where we're going to estimate parameters and determine sample sizes. So we're going to see how we can calculate population proportions and population means and analyze them. So a little bit about estimating a population proportion, and then the next section will be estimating a population mean. The point estimate, we call that the sample proportion. Is the best estimate of the population proportion. It corresponds to a single point on a number line, and that's why we call it a point estimate. We say that p hat is unbiased because it targets our population. So just some little things about the sample proportion here. The confidence interval, that's another term. It's an estimate of where the true population proportion lies. And sample size is your size necessary to estimate a population proportion. Okay, let's explore these concepts a little bit more. Starting with the confidence level. The confidence level, the most common ones are 90, 95, and 99%. And as a decimal, you can change them. So that means that they are what we consider 1 minus alpha. So alpha itself is 0.1, 0.05, and 0.01 correspondingly. And again, this confidence level is where we assume that our population proportion actually lies. Now, how do we interpret this? We say 95% confident that the interval from some number to some number actually does contain our true population proportion P. So he's going to be in there between two numbers, and we will have some percent of confidence that it's lying in there. The higher the number, the smaller the gap between those two numbers. And some more terms, critical values. If you remember that lovely bell curve, the standard normal distribution there. So when we're looking at some of the criteria here, we can sit there and say that the sample distribution of sample proportions can be approximated by that normal distribution curve. And our z-score is going to have a probability of alpha over 2 of falling in the right tail. So that's the little area under the curve. That's alpha over 2. So that means that the critical value here is called z alpha over 2. That's like the z-score for it. And then, of course, on the other side would be the negative z of alpha over 2. So an example, we want to find z alpha over 2 for a 95% confidence level. So 95% means it's between those two z's. We want the one on this end. 95%. Now here's how we go about that. We can use the calculator for it. It's finding a z-score, which is the inverse norm. Now you need your area. And since this is 0.05, so 95% corresponds to an alpha, which is 0.05. So that means alpha over 2 is 0.025. So I'm going to put the area in here, 0.025. And since it's standard normal, we know that the mu is 0 and the sigma is 1, and this is on the right. So that z alpha over 2 that we're getting is 1.96. That's this number here that corresponds to right there. It says this part over here is a probability of 0.025, 95% confident level that, and that's the corresponding critical value. Now, the next part here is just filling in a table because these are things that you need to memorize. The most common confidence levels are 90%, 95%, and 99%, which correspond with an alpha of 0.10, 0.05, and 0.01. And remember to find the z alpha over 2, or critical value. It's the inverse norm of your alpha over 2. So that's your probability right there, your area, comma 0 and 1 because of mu and sigma, and on the right. Okay, that's what we're going to be doing. So I put each of these in, these alpha values, into this formula, and I get the critical value for a 90% one is 1.645. For 95%, 1.960. We just encountered him. And 99 is 2.576. So make yourself familiar with this table. It makes your life easier. Now, margin of error. It's the maximum difference between the sample proportion and the population proportion. And that maximum difference is called error. Again, some notation down here. P is your population proportion. P hat is your sample proportion. The difference, that's the biggest difference between them, is the error. That's capital E. Your sample size, N, and Z alpha over 2 is your critical value. Formula for error is Z alpha over 2, that's your critical value, times the square root of P hat, Q hat over N. Now, we need to check some requirements before we can construct confidence intervals. So that it has to have a simple, random sample. And again, for the binomial distribution, that's bins, it has to have a fixed number of trials, 2 outcomes. It's like your P and your Q, success and failure, and the trials need to be independent. You need at least 5 successes and 5 failures because you've got to have at least a decent sample size. Now, confidence interval finding. You can use the calculators in the class. Those are the 84 plus to do this, or since I know both of you do a lot of your work at home, you can also use some of those stat calculators out there to find confidence intervals. These 3 formulas I'm going to write all mean the same thing. P hat minus the error. P is between that and P hat plus the error, or P hat plus or minus the error. And that means the same thing as P hat minus the error to comma P hat plus the error as an interval. So those are all three ways you can write a confidence interval. And remember, E is the critical value times the square root of P hat Q hat over N. Now let's practice some. We're going to construct a confidence interval based on some information. They tell us that they did a sample size of 1,487 adults, and 43% of them have Facebook pages. So A, we're going to find the margin of error with a 95% confidence interval. B, we're going to find the 95% confidence interval estimate of the population proportion P. And C, we're going to determine if we conclude fewer than 50% have Facebook pages. So margin of error. So remember, our formula is error equals Z alpha over 2. That's our critical value. Since this is a 95% confidence interval, that means Z alpha over 2, we memorized this now, is 1.96. Times the square root of P hat, that was the probability of a success, which was 43%, times Q hat, which is 0.57, because 1 minus P is Q, over N, the sample size, which was 1487. Pop that in the calculator, and we get the margin of error is 0.0252, so about a 2.5% margin of error. Confidence interval, and you can write it any of the three ways. I'm going to write it as P hat minus the error less than P hat plus the error. And one way to write that succinctly is 0.405 to 0.455. Part C, our interpretation. As you can see, based on the confidence interval, it does appear that fewer than 50% of adults have Facebook pages, because our interval is between, or is below 50%. Remember, it was 0.405 to 0.455. 50% is 0.5. So this is low, so yeah. The sample should be a simple random sample. No voluntary response ones. Your confidence interval should be provided, like 95%, that kind of thing. Your sample size should be provided, like 1,487 adults. And rarely do we even care about the size of the population. It's usually the sample size we care about. A couple more formulas. So how are we going to find the point estimate or margin of error if all we're given is the confidence interval? Because that happens. So what we do is we take the upper confidence interval limit plus the lower and divide by 2. That's how you get the P hat. To get margin of error, it's upper minus lower divided by 2. And why is that? Because I remember error is like that maximum difference. Now, how are we going to include this in ours? Let's look at an example. This says, of the 71 subjects, 70% were abstinent from smoking at 8 weeks, with a 95% confidence interval that ranged from 58 to 81%. So use this statement to find the point estimate and the margin of error. So point estimate is upper plus lower divided by 2, so like the average, mean. The margin of error is upper minus the lower divided by 2, which is 0.115. Now, sample size. What if, we do know P or don't know P hat, and we need to know the sample size needed. If we know P hat, then to find the sample size, we take the critical value squared times P hat times Q hat all over the error squared. If we don't know anything about P hat, the sample size, we can take the critical value squared times 1/4, 0.25, over the error squared. And so it's basically, I just rewrote the formula that we had earlier, which, if you remember, the formula we had earlier was for error is your critical value times the square root of P hat Q hat over N. So all I did is move that square both sides and solve for N. So just giving you an idea of where this formula, how it came about. Also, if you know P and Q, that's great. But if you don't, you can assume each of those is a half, because equally likely probability, and a half times a half is a fourth. That's where that 0.25 comes from. That's why if you know them, put them in the formula. If you don't, use 0.25. Okay, so now example. How many adults must we survey if 95% confident? The error is going to be no more than 3 percentage points. And we have, assuming that 80% make online, and then the other part's not any possible information about P and Q. So I'm just going to divide this down the middle and do the problem for both of the things we know. We assume P hat is 0.80, because that's what they make online purchases. So that means Q hat must be 0.20. Over here in part B, we know nothing about P hat or Q hat. Okay. Now, we do know for both of these problems that the error is 3 percentage points. And we also know that Z alpha over 2 for a 95% confidence interval is 1.96. Now, just going to plug those into our formula. Sample size is 1.96 squared, 0.80, 0.20, all over 0.03 squared. And I get 683 people. That's how many people I'm going to have to interview or poll or whatever. Now, if I know nothing about it prior, no P hat, then I still put in my 1.96 squared, but I put in 1/4 and still my 0.03 for my error squared. And this time I would have to do 1,068 people to be sampled. So if I don't have any prior information or assumption about things, I have to have more people. And this one, we're just going to identify a few parts to it. 1,000 respondents, 14% chose chocolate pie. Margin error is plus or minus 4 percentage points. So what do all these values represent? Well, 14% chose chocolate pie, so P hat is 0.14. Q hat must be 0.86. N is 1,000 adults. Error is plus or minus 4 percentage points, so 0.04. And P, of course, is our population proportion. Part B, if the confidence level is 95%, what is alpha? Well, 95%, 1 minus 0.95 is 0.05, so there's alpha. Which one's wider, 95 or 80%? Well, 95% is pretty restricted, so 80% is going to be wider. you're not as confident. So more numbers are included. Z alpha over 2, that corresponds to 90%. I told you to memorize those. That's 1.645. All right, now let's move on to our next part of our unit. I'm going to skip these examples because I don't think you're going to need them. So now I'm going to put us over to 7.2. Now what are we going to be looking at 7.2? Well, this is the estimating the population means. The last one we did the population proportion. This one's the population means. So in this section, we're going to look at methods for using a sample mean, that's X bar, to make an inference about the value corresponding to the population mean, mu. A point estimate, in this case, the sample mean, X bar, is the best point estimate or single value of the population mu. Your confidence interval, we're going to use some sample data to construct the confidence interval, and inside of it should be the true value of the population mean, which is mu. Your sample size, we just have to find the right sample size to contain population of mean in there. And then there's 2 instances where we have to consider in this unit where we know the population or the standard deviation and we do not know the standard deviation. The second case is really, or when we do know the standard deviation, it's actually very rare. So 2 cases. Part 1. This is when we estimate a population mean when sigma is not known. So the point estimate we were talking about. The sample mean is an unbiased estimator of the population mean. And that as the sample means tend to vary less than other measures of center, so it's going to be the best point measure. And we want to know how accurate our estimate is. We're going to have to start with that confidence interval. The confidence interval and some other notation. This is when sigma is not known. And our standard deviation is not known is what we're saying. Mu is the population mean, so X bar is the sample mean. S is the sample's standard deviation. N's our sample size. E's our margin of error. Now some requirements that we have. A sample has to be simple, random sample, and we are going to have it normally distributed with, and we would like to have n greater than 30 for our sample size. Some formulas for confidence intervals. When we had these same formulas earlier, instead of p-hats though, we're going to use X bars, because these are the sample mean minus the error, contains the population mean. Or the other way to write that is X bar plus or minus the error. And lastly, X bar minus the error, comma, X bar plus the error. Our critical value, that's T, because this is T distribution. T alpha over 2, the way we get that is the inverse T. And on the calculator, that's the second var's number 4. And if you need help with that, we can, or you can use, like I said, you guys usually do your work at home, so you can also use those calculators online as well for stats. You need to know something about degrees of freedom. We're going to use n minus 1. It's a sample size minus 1. A margin of error formula, it's going to be a little different than the last one. It's T alpha over 2. That's your critical value, times S, that's your sample's standard deviation, over the square root of n. And then our confidence level, again, it's either 95%, 90%, or 99%. If it's 95%, then alpha is going to be 0.05, 0.10, and 0.01 respectively. Now, degrees of freedom. The number of sample values that can vary after certain restrictions have been imposed on all of your data values are your sample size minus 1 or your degrees of freedom. It's basically n minus 1. So make sure we are noting this when we're doing our work in the calculator, because you don't want to have any problems with getting a z-score or a t-score confused. We're going to be dealing with the t-distribution, which is basically bell-shaped. So the normality, it's close to normal. It has the requirements loose, though. It's mostly bell-shaped or normal. Your sample size, we'd like to have it in is greater than 30, but between 15 and 30 is okay. And then we call it the student t-distribution, which is the same thing as when we abbreviate it, just the t distribution. And its formula is t equals x bar minus mu, so the difference in the two sample and population means, over standard deviation divided by the square root of the sample size. Now, I'm going to tell you, if you try to draw this t-distribution, it looks almost just like a normal curve. The mean is still going to be at t equals 0, just like the normal. The standard deviation is usually greater than 1 instead of equal to 1, and it depends on the sample size. The shape, again, it's approximately bell-shaped. It's not perfect, but it looks really close. And the sample size, we like to use n greater than 30. Now, what did we mean by this? The standard normal is the green one on here. The purple one is really close to it. It has a higher sample size than the blue one, and so the bigger the sample size, the more standard normal it becomes, is what we're saying from this picture. Now, what do we know about confidence intervals and stuff? So some things we need to know. We need to have the verifier 2 requirements were satisfied earlier. With sigma is unknown, we use n minus 1 degrees of freedom, and we use our calculator to find the critical value, which is t alpha over 2. It corresponds to our confidence level. To evaluate the margin of error, we use the formula E equals t alpha over 2 times s over the square root of n. And we use that margin of error in the value of the sample mean, which is x bar, into one of the formats for finding the confidence interval. To round this, if we're using the original data set, use one more decimal than given. If we're using a summary of the data values, use the same number of decimal places as the sample mean. Again, here are some steps for using on the calculator in the classroom to find a confidence interval. However, if you want to use the one at home, like on the computer, you can use that, because I know that you guys are using those stat calculators instead of the ones in the classroom. Now, finding a critical value t alpha over 2. So we want to find the critical value corresponding to a 95% confidence interval. We know this is a t distribution because we're looking for t alpha over 2. And we know the sample size is only n equals 15. So in the calculator, we would do inverse t, because this is a t distribution, our area. So again, we have to do the same thing we did earlier. 95% corresponds to alpha is 0.05, so alpha over 2 must be 0.025, okay? So I'll put my area in there, 0.025, comma, my degrees of freedom. Now my degrees of freedom are n minus 1, and n is 15, so 15 minus 1 is 14. So this tells me in the calculator that it's 2.145. And that is, again, my critical value, which is T alpha over 2. So again, I had the area here, and remember that critical value is that line there. That means 95% confident that it lies in there. The population, or not population, the sample mean lies in there. Confidence interval using birth weights. Okay, so we have a bunch of birth weights. This is sample data, and we're going to construct a 95% confidence interval for the mean birth weight of girls. So how are we going to do that? Is the sample randomly selected? Well, yeah, all those numbers were randomly selected. So check. Is the population normally distributed in a sample size greater than 30? And there's probably not on here. So it was n equals 15. But remember, we said we could use it between 15 and 30 if we had to. Now, remember, this was a 95% confidence interval. So 95% corresponds to an T alpha over 2 equal to 2.145. And our formula goes, we take our critical value times our, in this case, we're looking for our standard deviation. It gave us that in the problem, S. So I'm going to go ahead and write that up here. That's another thing given to us. S was 2.9. So times 2.9. Well, that does not look like a 2.9. Over the square root of n. N is our sample size, which was 15. And remember, this is our error. Pop all that in the calculator, we get 1.606. Now, according to our problem, our X bar was given to us as 30.9. They did all that out of those listed data for us. That was nice of them. So what we're going to do to get the confidence interval is we're going to take 30.9 plus and minus 1.606. And that tells us our confidence interval is 29.294 to 32.506. So we constructed a confidence interval. Now back to what does it mean? Confidence interval says if we are 95% confident, that's if we're using a 95% confidence level, that the interval from, and it usually has two numbers, actually does contain the true value of the population mean. Some more formulas, similar to what we had earlier. X bar, that's the point estimate of mu, and margin of error E. Look at that. It's your upper confidence interval limit plus your lower one divided by 2, and this one's your upper minus your lower one divided by 2. More notation. Mu is your population mean. Sigma is your population's standard deviation. X bar is your sample mean. E is your margin of error. And Z alpha over 2 is still your critical value. Notation is going to stay the same there. Back to sample size. Now let's talk about sample size. We usually have to figure out how big something's going to be able to deal with it. So we're going to check the sample as a simple random sample, and we're going to find the sample size. How do we do that? N is Z alpha over 2 times sigma, all divided by the error and squared. So when we compute this, you obviously need a whole number that we have to round up to, because you can't have part of a person. Okay, assume we want to estimate the mean IQ for the population of stat students. How many stat students must be randomly selected for IQ test if we want a 95% confidence interval that the sample mean is within 3 points of the population mean. There's our formula down there already typed. So Z alpha over 2, remember 95% corresponds to a Z alpha over 2 of 1.96. And then our sigma, we're going to have our sigma in this case, 95%, 3 points of the population mean. So sigma, oh, we used it before. That's how I was going to say 15, because it didn't tell us sigma here. So yeah, for IQ, we've used the IQ test problems before. And so I think their mean is at 100. And then either side of that, going a standard deviation of 15. That's where I'm getting this 15 from. Previous word problems. 3 IQ points on either side, and then squared. Put that in the calculator. We need 97 students to be able to do this. What did it say? Of all the thousands of students that are out there, we need to obtain at least 97 of them for the sample. With a random sample of only 97, we will be 95% confident the sample mean is within 3 IQ points of the true population mean. All right, now we've made it to part 2. Part 2 is actually very rare. It's when sigma is known. It's a margin of error. In the real world, we have to deal with things that are known. Sometimes we have to look at this margin of error here. I mean, we usually deal with things that are unknown, so this one we don't know much on. So part 2 is talking about our margin of error being the same formula basically, except it's the margin of error is the critical value times sigma over the square root of n, and this is what we use when we do know sigma. You could tell it's getting really late. I'm stumbling with my words. So we're going to still use the same 15 birth rates we had earlier for the girls, which gives us n is 15, x bar was 30.9, and it wants a 95% confidence interval. And they say sigma is known to be 2.9. So what we're going to do is we're going to check all of our requirements, and they were satisfied. And then we're going to actually find this with the error down here. I've got the error formula. So error is our critical value for a 95% confidence interval is 1.96. Our sigma, in this case, is 2.9. They give that to us. Over the square root of n is 15. Put that in the calculator, we get an error of 1.46760. Now our x bar, we know that was given to us is 30.9. And with our error, we can actually find our confidence interval. So our confidence interval is 30.9 minus the error. It's 29.4. Add them together to 32.4. There's our confidence interval. It's somewhere between 29.4 and 32.4. Now, how do we tell which distribution to use? Because I told you in this lesson we used a T, and then all of a sudden I started using a Z. All right, so here, what are we doing? If sigma is not known and we are normally distributed, use the T. If sigma is not known and n is greater than 30, we use the T. This was part 1. Okay. If sigma is known and it's normally distributed, use the normal distribution. If sigma is known and n is greater than 30, again, use the normal distribution. That's part 2. If the population's not normal and n is smaller than 30, then we'll use something else. We are not doing any of this right now. So it's either you know sigma or you don't. You hope you don't know sigma, because then you can use the T distribution. In the rare cases where you actually do know sigma, that's part 2. And guys, that is the end of our notes for Chapter 7.